All right. Okay. So today's talk is on interpreting spectrometry and spectra. So that's a lot. So really it's interpreting spectra from a modeling perspective, because I primarily do atmospheric retrievals. And because I really care about clouds, I'm going to put a lot of perspective in interpreting clouds in your spectra. So the big thing to think about when you want to interpret your spectra using a modeling technique is really, what is your science question? And so it's really important to think about what your question is as you can craft thinking about which tools you want to use. And so things you want to think about are, what are the key bits of information that you want to explore through your modeling? So for me, I do atmospheric retrievals. So something I think about a lot is constraining the thermal profile. Along with that, I think about getting out the chemical composition, getting abundances for gases in my atmosphere, using that to tie back to understanding information evolution. Some things you might think about, which are in green, are maybe you care about chemical abundances and getting accurate ones. Maybe you think there's this equilibrium chemistry going on in your atmosphere, and you want to be able to constrain that in some way. Maybe there's vigorous vertical mixing and you want to mention how much there is. Maybe you care about the C to O ratio for formation. I know we've talked a lot about C to O ratio. That could be a thing you're going after. Maybe you have high resolution data and you want to get isotope log abundances. Other things I like to think about are clouds. So when thinking about clouds, maybe you want the size of your cloud particles. Maybe you're thinking about cloud composition, maybe variability, because you're seeing something going on in the atmosphere and your spectra that points towards that. Maybe you just want to find a model that matches to your data and you want to get out some fundamental parameters. Maybe you want a temperature or a radius, et cetera. Maybe you want to use your models to predict information on wavelengths that you don't have. Maybe you're putting in a proposal, you've got near infrared data, you want to go after some MIRI MRS, since we know it's going to die soon, compared to other modes. Maybe you want to say, this is what I might see out there. Really important. Maybe you have some unexpected features in your spectrum and you're just trying to figure out how to fit those. And there's probably more science questions you have. So you really need to think about that when deciding which approach you're going to take and how to best use that modeling tool. Particular when thinking about clouds, right? We have this wide range of clouds in the atmospheres of these substellar objects. As you move down, you're moving to deeper, hotter, denser layers. So in particular with your modeling tools, if you're going after clouds, you need to make sure the kinds of atmospheres you're looking at, those particular cloud compositions are in your model. Okay. And with clouds, we know if we look at color magnitude diagram, we have these wide range of J minus K colors. And as you're moving down, so we have the brown dwarf sequence, and we have a couple of directly imaged exoplanets off to the side. As you move down, you're starting to see the emergence of those silicate clouds. And as we move quickly across similar magnitudes, different J minus K colors, you're starting to see a region where you don't see any clouds at all, as the silicate clouds are dropping below the photosphere. And then as we move down along this side, we're starting to see the emergence of sulfide clouds and down to these water ice clouds. Additionally, when we think about how clouds impact our spectra, we have to think about where they are in our atmosphere. So this is a great plot that's in Birmingham et al. 2017. Don't know why it's not showing up. Depending on how deep your cloud is in your atmosphere, it's going to change what you're seeing for the features in your spectra. So the higher up the cloud is, the more it's going to be washed out, and the deeper down, more of the features you're going to be able to see. And so when I think about modeling, there's two big techniques people are using right now. There's either forward modeling or retrieval modeling. And you can think of these things as two opposite ends of a spectrum. And so with forward modeling, we have these self-consistent grid models. They are trying to put in a lot of your physics and chemistry, and you end up having few knobs you can turn to fit your data. On the complete opposite end are free retrievals, where the only thing you're putting in is your radiative transfer, and you have many, many, many knobs you can turn. And so that allows you to really fit your spectrum really well. But you can end up with bizarre things that come out, things that might be unphysical. So it's really important to look at your results really critically when you're doing that. And as you move along, there's a range of models in between that you can use, such as chemical equilibrium retrievals. So you're kind of just decreasing the consistency across your models. So to get a little more into forward modeling, you've probably also heard those as grid models. These are self-consistent models that include all of the physics and chemistry. So here is an example of pressure temperature profiles. I'm going to show a lot of them today. You're moving higher up in the atmosphere to deep down, cooler to hotter. And in these forward models, your models include and assume radiative equilibrium. So here we're showing thick regions where you have internal heat flux and convection, and then the thin parts of the profile is where it's radiating out of your atmosphere. You have your chemistry and thermochemical equilibrium, and you tend to have quench approximations. So there are regions where your gases are going to change depending on temperatures of which ones are chosen. So particular thinking about carbon monoxide versus methane. And so the point where they're switching is that quench point. There is a really great review from Barley and Robinson in 2015 that tells you a lot about forward modeling that I will point you to. And there was a really good talk by Heather Knudsen in 2018 at the Sagan workshop that has a really good slide on forward modeling. So what do forward models include? So when you end up having this grid of models, you typically find parameters such as effective temperature, surface gravity, metallicity, C to O, KZZ, which is the eddy diffusion coefficient, and that sets your particle size. And then this value F sed, which is the sedimentation efficiency. So that is a way to parameterize your clouds. If you have a low value, you end up having thicker clouds, and a higher value gives you thinner clouds. So we're just showing kind of differences in what the spectra looks like when you start tweaking these things. Tweaking temperature, you see big differences. Here, it's just differences in the surface gravity of your object at those different temperatures, metallicity, and then C to O ratio. So they can make minor differences, but they're pretty important ones when interpreting your spectra. And so why would you want to use a forward model? Forward models are really easy to compare to observations. There are tons of publicly available forward models out there. This is just a smattering of ones I thought of while I was writing this talk. Also on this link is a bunch of other forward models you can find, as well as other modeling tools for looking at spectrum. They are great when you have limited data coverage. If you only have a few photometry points and you want to say something about what could be going on, forward models are ideal to use to fit that. They're ideal comparisons for retrieval fits. We're going to go into retrievals in a little bit, but really using a combination of both of these modeling techniques can tell you different things about what's going on in your atmosphere. There's plus and minuses to both sides of the models you want to try. And they are great predictions for proposals. So what are atmospheric retrievals, right? This is, again, that opposite end of the spectrum where it is a theoretical inverse spectral modeling technique that makes minimal assumptions about physics involved. So that was that big mouthful. So just a reminder, that's the opposite end of the spectrum. So for the retrievals, the completely free ones, the only thing you're requiring to be consistent is your radiative transfer. And you can allow your model to do crazy things for basically anything else. So you end up having these tons and tons of knobs you turn. And so these two models, you have these chemical equilibrium and free retrievals. And so I'm not wanting you to actually read what's in these corner plots, but you can see that there's tons and tons of parameters in your free retrievals, or typically for your abundances, we are assuming they're uniform within the atmosphere across the entire altitude. So that's usually not physically motivated, but it allows you to have all of these knobs. So you can say exactly how much methane do I have, or how much ammonia, et cetera. And it puts in many, many parameters, and that allows this really tight fitting of your data. The thermochemical equilibrium retrievals Those instead pull your chemistry from a thermochemical grid, and the only thing you're retrieving on is a metallicity and a C/O ratio. So that greatly reduces the number of parameters you have, so that speeds up how quickly your model runs, but those don't tend to fit the data as well because you don't expect everything to be in chemical equilibrium. So how do retrievals actually work? So what goes into your retrieval model, right? It's this inverse technique. So you're starting off with your data. Based on this data you have, you can come up with a list of gases that are in the atmosphere. And so this is really just based on the data you have. Weird things can happen is if you put in gases that you expect to be in that atmosphere, but aren't visible in the spectrum you have. So if you put in, say, CO2 where you don't have a CO2 feature, sometimes retrievals will try to fit that with some other parameter. A cloud might try to mimic some of that opacity. So those are things to really think about and be careful. You end up parameterizing a lot of things. So how you're handling your pressure temperature profile, if you're putting in clouds, how you're parameterizing them, what parameters you're going to try to get out, how you're handling your chemistry. And then in every retrieval model, depending on which ones you use, there's a large variety. They all have underlying assumptions that don't change between each of your model runs. So how they're treating radiative transfer, those can vary. And where you're getting your gas opacities or your line lists. And that's going to be a big difference between some models. There's definitely been some work, particularly talking about methane line lists and others where you want to, make a decision on which ones you want to use depending on the resolution of your data. So you're wrapping this in some kind of sampler. A lot of retrieval models are going to use either MC or nested sampling, but really how the sampler works is you're taking your data, so I have those as the points, and you're fitting some model to it. And so for every single parameter in your model, you're trying to quantify how good that model fit is. So we're going to just show two here, water versus CO. And so here we have a model. It looks like it fits pretty well. And so what the model is going to do is you're going to take a step in your parameter space and you're going to test another model. This one, not a good fit. We're going to do it again, try a different one, a bad fit. So you're going to do it hundreds of thousands, even millions of times until you can come up with regions where you're likely to find good fitting models and where you're likely to find poor fitting models. So that's going to set up your confidence intervals. And so you take these and you can transition that into getting out values for each of your parameters. And so what you actually have on the x-axis is your C/O abundance versus the probability of having that value. And so your confidence intervals, you get your peak giving you that abundance. And what you have for your plus or minus is your plus or minus 1 sigma confidence intervals. And so you end up doing that for all of the parameters that are in your model. And that's how you get out those abundances in these many corner plots. And so what comes out of the retrieval are your gas abundances, depending on if you're doing them individually or your metallicity and C/O ratio. You're getting out your thermal profile and cloud properties if you include a cloud. And then the last thing you're getting is your retrieve spectrum. And the spectrum tends to fit your data really well because you have all of those knobs you can turn. If you're thinking, great, I want to use retrievals, these sound like the hot thing to do. Everybody's using them. I got data. I want to run some. What retrieval models should I use? There's at least 49 codes that are published in this repository. This is the Exoplanet Atmospheric Retrieval Code. It's on codes list. It's on Zenodo. Ryan McDonald compiled this. It's showing the names of the codes, if they have names, or what papers they come from, to use MC, nested sampling, etc. What uses are they for? Not all retrieval codes are built the same. Some handle transmission data only, some handle emission. There's a few that do reflection and then references to these codes. Not all of them are open source, so that's also going to be a thing to make a decision on if you want to use them. Thinking about directly imaged exoplanets, some good retrieval codes to use. Brewster is open source. That is the code I use. It's out there on GitHub. It's a little hard to find, so if you want to find it, you can also ask me that question. Chimera has been used a lot. I don't think that's open source though. If it is, it's a little hard to find. I think you've probably heard of Petit Radtrans. That one is all Python, really user-friendly. There's a lot of documentation for it. And then Helios has also been used. Okay, so I told you briefly about forward modeling versus retrieval modeling, but the question you probably have is, when do you choose to use a forward model versus choosing to use a retrieval model? And so it really comes down to your science question and also what kind of data you have. So I'm going to use beta pic B as an example. We all love beta pic B. Here is GPI spectrum and gravity. Maybe we don't all love beta pic B. Maybe that's what was up there. It's a love-hate relationship. So plotted in purple is a forward model fit. Two big things to think about when you're looking at your data is, what is the wavelength coverage you have and what is the resolution? If you have very few points over a very small wavelength range, you probably don't need a model where you're turning tons and tons of knobs. A retrieval's probably overkill. It's going to give you many different things that can fit that limited amount of data, so you probably don't want to use that. That's probably when you want to use a forward model. This is a great forward model fit. I tried to do some retrievals on this. GPI data is its own can of worms. Retrievals are also their own can of worms. So particularly retrievals are going to be more powerful the more data you have. You're going to be able to fit more features, get a lot of information out. Additionally, I won't be giving this talk, but in plug, brown dwarfs should be your friends. They are awesome. There is beautiful high resolution data for brown dwarfs. There's this wonderful overlapping region between brown dwarfs and directly imaged exoplanets. So another way to think about interpreting your spectra is to compare them to analogs that are similar in temperature or spectral type that have additional data. So as an example, I want to show a brown dwarf that's in black in both of these figures. It's WISE 1243. And so in this Ferry et al. 2021 paper, they're comparing it to the HR 8799 planets, and you can see there's some similarities between them, as well as some other brown dwarfs. And they're using that to really kind of get at what's different on this object from other brown dwarfs, and also what's different and similar to these directly imaged exoplanets. So that's always another way to kind of start interpreting your data, pull out, okay, maybe I don't have enough information on my object. What else could I use to compare to? Maybe you have that beautiful spectrum of VHS 1256b from JST. That thing is rich, full of so much information. But for a retrieval, that is too much information, right? There's also this thing called computation time. Trying to run full resolution retrievals on the full data set is something that we have not been able to do. As part of the ERS team, we've decided to bin down that data to try to run it over the entire wavelength range. So that will give you a really good handle on the pressure temperature profile. You need wide wavelength coverage to get that pinned point down really well. And some other things you can do is say, I really want to focus on, say, the 3 to 5 micron range where I want to get at methane, CO, get towards that C to O ratio. And there are a lot of people that have been running retrievals on high resolution data on a limited range and comparing that to results that they get out from forward model fits as well as retrieval fits over longer data coverage. It wouldn't be a talk without including this great feature of the silicate clouds and how rich that is and how much so that can be done with high resolution and low resolution data. So I want to talk a little bit about a few different case studies to kind of place this modeling in context. We're going to talk about interpreting clouds in the context of wavelength coverage and resolution of your data. I also want to talk about a few studies that look at the chemical abundances and the interpretations that come out of that in the context of the wavelength coverage they have and how they parameterize their pressure temperature profiles, because that also can make a difference, and the bizarre unphysical results that can arise, Retrievals don't always give you the correct answer. What they tell you is what is definitely not the answer for your data. Retrievals aren't these magic knobs that tell you something. It's really that precise science question you have is how you want to handle it, because you can't run infinite models to definitely know what it is. You can say something about your science question and your object, the answer that it is based on the data you have. So thinking about when you have limited data coverage, this work from Anna Luber in 2022 tried to look at a sample of LNT dwarfs with spectra and use a free profile to fit them. And things that came out were with this limited wavelength range. They also tried the full wavelength range and also cut off pieces of the spectra to see how that changed their models. They fit cloudy and cloud-free models, and they could not tell the difference between them. For early L dwarfs, they found that gravity they got out of the models depended on which cloud model they used. They tried various permutations of the data. They changed gases they put in. They changed the wavelength range. And they also found that constraining the optical depth depends on the priors that are in their models. So picking out a retrieval code and using it is not enough, because you also need to understand what priors you're putting in and what biases you're baking into that model. If you say know something about the radius of your object because you've got a dynamical mass, so you can get out a radius, you can put a tighter constraint on that. If you don't, you probably want to leave that wider. So each of the different retrieval codes, the person who's written it and before you've used it has made some decision on what their priors are. If you're going to be using it, you also have to think about that, because that can give you differences in your results. And when you have that interpretation, it might just be based on a choice in the model setup. Some work I did in 2020 and 2022 is I looked at a sample of brown dwarfs of the same effective temperature, and I wanted to look at differences between them. And so here I did a couple of models using Specs Prism data. And again, I found some objects that have these models where you cannot tell the difference between a cloudy and a cloud-free profile. They tend to swoop down in the deep atmosphere. That's typically something we see when your retrieval model probably wants you to try a cloud. But for some objects, you get this. And a big thing I noticed was if I only cared about the C/O ratio and the metallicity, it didn't actually matter which cloud model I used. Those values came out really consistent across a variety of models. So if your question is just, I really want to pinpoint down my abundances, then maybe you don't care about getting your cloud model super accurate. Maybe that's okay. A different work looked at the near-infrared data of an object. So this is Ben Burningham's 2017 retrieval paper for the unusually red brown dwarf 2224. And they did a retrieval fitting just this near-infrared data from 0.8 to 2.4. So the data is in black. We have what came out of the retrieval in yellow, and it's on each of the individual draws in red. And then in magenta and aqua, we have the forward models. So you can see the forward models really struggle to fit this object. And in particular, forward models have a really hard time with outliers, things that are unusually red and usually blue, metal poor. So if you're finding a poor fit for one of your objects, that might be a time you want to try retrievals. A retrieval does a really good job, but this object has data out in Akari data as well as Spitzer. So it's got long wavelength coverage. They said, all right, let's take our retrieval model, make a prediction and see how does it fit the data beyond what we fit on in our retrieval. It doesn't do a great job. It doesn't fit that silicate feature, but neither do the forward models. And so if you're really trying to get out some of these features, you probably want to include additional data in your retrieval model. In particular, the big thing that came out of this is finding that the shape of the pressure temperature profile is really driven based on how much data you have. And so in the 2017 work that used just the near infrared data, it looked like this black line. And when we went back in 2021 and tried to include all of the data in our model, it completely changed the pressure temperature profile. So now it looks like what's in aqua, and then the green dash line is from one of those forward models. So they're starting to align, but there's still a mismatch in the upper atmosphere. So that can also inform you what might be missing from your forward models or what might be missing from the retrievals. So they're a really powerful tool to use in tandem. And when we fit the entire wavelength range, we then were able to fit the silicate feature. And so this model had like 45 different parameters. I think Ben ran 64 different models that ended up in the paper. That's probably overkill. I don't tell anyone to like throw an entire kitchen sink of models at their object. This was like 5 years worth of time and energy. Retrievals take super long, but this, because you have all of this wavelength coverage, you can fit the pressure temperature profile really well, and you can start to characterize exactly what kind of species your clouds are made up of. So in this model, you have a deep iron cloud, and co-located in space are two different silicate clouds. You have MGSIO3 and MGSIO4 higher up in the atmosphere. And so this broad wavelength coverage is allowing you to probe many orders of magnitude in pressure space of your atmosphere. If you have limited high resolution spectra, and maybe you have some low resolution, great work by Jerry Schwann in 2022 was looking to see, well, what does the high resolution data tell me versus what the low resolution data tells you? And so he did a retrieval using K-band K-pic data. So that's 2.29 to 2.24. So a really small regime. And then he also ran low resolution retrievals, the data separately, and then combined them jointly. And what they found was that the high resolution data was insensitive to clouds. Even though you're probing a lot of these line cores, getting deeper down, because it's such a short wavelength range, you're not getting enough information to really probe the cloud features you have, right? If you're looking at these silicate clouds, you need those longer wavelengths out between 8 and 10 microns, and this region is not getting that. He found, even though they're insensitive, the parameters between his cloudy and cloud-free models were nearly identical. And due to the small wavelength range, and cloud opacity dropping to negligible levels in that continuum. So plotted over top in black is a contribution. So where you're probing based on, this is the high resolution, and then this is the low resolution data. Along with spectral resolution, and coverage, these things are also important. So Callie Hood did some work in 2022 looking at the exact same object with fire SXD data versus Specs Prism, covering essentially the same wavelength range, and ended up finding that you get some big differences in your abundances. So here you have the initial specs data in blue. So you have this really wide range in what you're getting. The higher resolution data tends to give you tighter constraints, but particularly for water and methane, you can see it's shifted by quite a bit. Same thing for ammonia down here. So again, with your question of what can my data tell me now, you might get a big shift in your gas abundances depending on your resolution. So if you really want to go after that and you want really tight constraints, you probably want to make sure you have that high resolution data. Callie also did some recent studies with JST data and saying, well, what happens if I combined individual combinations? So running a retrieval using the 3 to 5 micron G395H, you can see it fits the data really, really well. And the big thing that came out of this was You can use a JST spectra, but you really need to probe the near infrared to get deeper down in your atmosphere. And so the JST plus specs, this darker green, makes a big shift in how your fit is, including the additional long wavelength data. Gave a little bit more to the retrieval, but not a significant amount. So you really need to make sure you're covering particular wavelength ranges to get tight constraints. How the pressure temperature profile is parameterized also can impact the results. So this is work from Harshal, who is somewhere in the room. I'm pretty sure this exact spectra is on his poster. You should go check it out. This is a wonderful Wydorf WISE 0395. Beautiful retrieval covering the entire wavelength range. And he tried a variety of pressure temperature profiles and found using the two different parameterizations, they led to some different values in your abundances. So it feels like it's maybe overkill as I'm repeating all of these different things that can change your abundances, can change your constraints. It's a lot, right? So these are things that you need to consider in your retrieval modeling. We also can get to weird things that come out. I ran some retrievals on a low metallicity object, and I had a variety of models that were indistinguishable. Here I'm showing the retrieval fits in, again, yellow, and then the models are in the bright colors. The grid models really struggle. Again, this is an outlier. These unusual objects don't tend to fit well. So the retrievals can do a much better job. And so again, this is just zooming in the retrievals, but I got some really weird things out that are totally unphysical. So I just want you to focus on the mass in this table. These four retrieval models fit the data really, really well. This is an old low metallicity object. We expect its mass to be closer to the order of 70, 75. You get to a super low metallicity run and you get a mass of 30. I don't believe that. Even though the models say these are indistinguishable, you shouldn't be able to tell the difference. This is when you need to start using your judgment on what is really physical. Retrieval models tend to give you really small radii. We said that the grid models don't struggle to fit some of these outliers. Retrievals are a problem with small radii. You can get some mismatch on physical parameters. There's just a lot that are going on. So really important to think about them critically when you're analyzing your results. Also, a really important thing to do, which is starting to become more of a thing in the community, is to run multiple codes on the same set of data to try to compare the differences that we have. So I just want to leave you with two key takeaways. And so things to think about are when you're looking at your data, deciding between your forward models and your retrievals, what wavelength coverage and resolution do you have? Keeping that in mind with your science question. And then your retrieval results can't be blindly trusted. You really need to check if your results are physical. I'll leave it with that.
Yeah. Yeah. No? Yes. Yeah, anyway, if anyone has questions, we have a few minutes for questions. It doesn't work. Any questions in the audience? Thank you. Yeah, otherwise okay. It's okay, I can run back and forth.
Hi, it's from Leiden. I was wondering, there are there's some ground-based instruments that do 3 to 5 micron spectroscopy, low resolution spectroscopy. Do you feel that this should deserve a bit more focus before METIS on the ELT comes online to help you with understanding and retrieving better models for our exoplanets?
Yeah, sorry.
Great. So should we be focusing on ground-based 3 to 5 micron spectra? Yes, I think it's really important. From the retrievals that have it, it's really done a much better job in getting you tighter C-to-O ratios. So if that's a thing you want to try to go after, I think that's a really good thing to focus on to add to the retrieval models.
Oh, Marcus? Yeah. Top left. Oh, no. Okay, I was thinking, I saw Marcus in the back. But we can start with that person in the middle here. Sorry about Yeah, it is working. Okay. Sorry, do you mind passing the microphone?
Okay, thank you. Thank you for a great talk. My question is about we have so many models, and how do we interpret the differences between models if they are all physical? So, like, how can we choose a better one or best one?
Okay, so if you have a whole bunch of models, you have results that come out that are pretty physical. How do you decide which is the best one? Typically, if you're doing nested sampling or MC, you're using the Bayesian information criterion or the Bayesian evidence. So that will tell you which model is the best fitting one. There is a scale to use, typically with the Bayesian evidence. If it's greater than 2, your model is not rejected, but it's strongly preferred to have the higher Bayesian evidence. Same thing with the BIC. So if you have things that you by eye, you typically end up looking at things yourself. By eye, you can't distinguish them. It's usually the BIC or the Bayesian evidence that tells you which is the better model for your object. If you're trying to tell differences between different retrieval codes, that's when you're going to get down to comparing, each of their best fitting models, maybe digging into, have you used different line lists? If you're looking at high resolution data, did you change the resolution for fitting your models? Typically, you want to run your line list between 10 to 100 times higher than the resolution of your data. Those can make tiny differences. I think the transiting ERS data, they did an intense discussion on how high you need to use and what that changes. So there's like lots of small things to then start thinking about in the differences in what the priors for each of those models for the different retrieval codes were at that point.
Yeah, we can have a last question. It's okay. Let's introduce yourself.
Hey, Markus Bonser from ETH. I have a question for this last point, also on the takeaway slide, that the retrievals can produce maybe non-physical results. Is there ways, if you can run a retrieval and in the end judge that it's non-physical, is there ways to run a constrained optimization procedure instead of a blind MCMC to make sure it's not running into the non-physical results at all?
Good that you have time to think about the answer while I'm running back to you. I mean, running is a big word, but yeah.
So is there a way to put prior constraints on your model to make sure it gives you physical answers? Yes, you can. So for a lot of the retrievals that have been done, I've given it things that should be physical. but it will push up against the edge of your priors because it wants to do a trade-off. So for a lot of these brown dwarfs where you get out really small radii, you're tending to get higher temperatures because that's the trade-off in the model. You could tighten your radius constraint and they'll lower your temperatures and try to fit the data as well. But then it's going to try to turn a different knob in your model to bump something else up. So you have all of these different knobs to turn, and it makes it a little bit harder. So the more information you have, like if you had a tight radius constraint from something else, you could force that into your model to try to give you something closer to what's physical.
For your answers and for your really cool talk. So let's thank Eileen again.